So this chapter is about ratio games, and the word game here is used in the sense of the competitive spirit in the industry where you are competing with somebody else and you want to show the performance, your performance is better than theirs, and so people do certain tricks, and that's what we will talk about here as ratio games, as opposed to not for so much for entertainment, it is more for competition. And so we'll give you start with an example, and then we will show you how it can be done with metrics, with the relative performance improvement, with percentages, and then what are the guidelines, and then when you know that there is a problem. So we already did a similar question, similar examples in the very first lecture, but here is one more. Is that and this is a case study. So actually that means these are real numbers. So system 6502 and 8080. Anybody has heard of 8080? What is that?
Isn't that the processor before 286 or 386?
Yeah, good. All right, so this is a processor that was used before 286, or maybe there was 186 even. So this is Intel processor, and then there was 6502, I think that was Motorola processor at the same time. So people compared the performance on two benchmarks, which are Block and the CIF benchmark. If you read the chapter on benchmarks, if you didn't read them, then these words will not make sense. Please read them before the exam, because it won't make sense. But anyway, so these are two benchmarks, two well-known systems, two well-known benchmarks. You have this performance. If you take the sum and the average is 52.17, and I should indicate that this is the time it takes on the benchmark. So that's important, because so lower is better. So 52.17 on 6502 and 8080 is 49.79. So the conclusion of this is that 6502 is worse. It takes 4.7% more time than 8080. Agreed? Right? Now we do the other way, where if you are a 6502 person, if you are Motorola, was it Motorola 6502? Okay. Anyway, then you would take the ratio with respect to 6502, and you say 8080 is 1.25 slower on first benchmarks, and only 76% slower on the faster actually, or slower on the second benchmark. So on the average, it is 1% slower. Right? And if you are 8080, you just do the opposite. And the opposite is that you take yourself as the base, and then you say 6502 is 6% slower. Now, which of these three is the right answer depends upon which company you work for. Right? But the good thing is that we will teach you some rules, so that as soon as you look at these things in a paper, you know that there is a game here, there is a problem here, and that if we change the base, the answer will change. By the base, everybody understands what is a base. Whatever goes in the denominator is called the base. So here 6502 is the base. Here 8080, so that goes in the denominator. We take that number and put in the denominator, and so on and so forth, right? All right, so here is a very famous paper. RISC. Anybody has heard of RISC systems? RISC processors? You have heard? What is a RISC processor? You, yeah.
Okay, it's I know the difference between the RISC and this RISC is the simplest assembly instructions.
Right. Reduced instruction set computer. So there was a time when there was a big debate whether RISC is better than CISC. Normal computers are CISC, which are complex instruction set, and then RISC is reduced instruction set, simple instruction set. And so the people who invented RISC, they published this paper in IEEE, ACM, some big magazine, and they took 11 different benchmarks, and they took 6 different processors, and they took the sum and took the average. Actually, they didn't do this one. So basically, I'm doing this right now. Okay. So if you take the sum and take the average, your conclusion is that the RISC has a very large code size. And the code size is simply measured in the number of instructions. So this is the number of instructions, right? And so you need 2360 instructions for the RISC. On the G8002, you need only 2140, and and so on and so forth. So Z8002 requires 9% less code than RISC 1. On the other hand, if you take RISC as the base and do the computation, you will come out that Z8002 takes 18% more code than the computation, than the RISC. Okay, this was published in 1982 in a very prestigious journal. I think it was ACM Communication or something like that. And obviously now you can work out the other way around, where you take, if you are G8002 company, then you will take that as the base and go on and do and come with another conclusion. So these are the real things that people have done. Now it turns out that this was not deliberate. People who wrote the paper, they're my friends, and they didn't understand this whole ratio game thing at that time. So without realizing, they did use this ratio. They did use the ratio exactly as presented here, and they showed that RISC is better. So sometimes this happens, right? So you just don't want to get caught into things like this. So here is the one where the ratio is clearly could have been done the other way around, and people could have bugged it out both ways and seen if the conclusions are counterintuitive, are counter to each other, which they didn't. But sometimes the ratios are built into the metric, so you don't have to do this. For example, throughput and response time. Network A has a throughput of 10 and response time of 2. Network B has throughput of 4, response time of 1. But somebody may not even present you the throughput and response time. They may just present you power. And they could say, well, system A has a power of 5 and B has a power of 4. Right? And so here I think if you just use the throughput metric, you would say the system A is better, higher is better. If you just use the response, throughput is 10 is better than 4. On the other hand, if you use response time as a metric, you would say that B is better than A. Right? So why get into that debate? Just use the power, and then you can say, well, A is better than B overall, with considering both throughput and response time. The power is the best criteria to combine these two, and then we get this one. And somebody may come up with the opposite metric, which is response time upon throughput and so on and so forth. So the idea here is that sometimes the metric itself is a ratio, and that can cause this kind of problem. Sometimes the ratio is built into the system metric. So another way of saying the metric is in the metric actually is that you are measuring an accelerator, 2 floating point accelerator, and you say, well, when I used the accelerator A on machine X, the performance went up by a factor of 2. It went from 2 to 4. When I used accelerator B on machine Y, not on X, I used accelerator B on machine Y, its performance went from 3 to 5. Now the ratio with A was 2, with B it is 1.66. So which accelerator is better? Which accelerator is better? Obviously, with this data, you would say A is better, right? But what is wrong with this data? The problem is that these ratios are not comparable. This is on X and this is on Y. The bases are different. The numbers that you are dividing by here, the denominators are different, right? Because the machines are different to begin with. If the machines were same, then at least the numbers are comparable. But here we are just comparing ratios which are not comparable. And then other times they show up as the ratios also show up as percentages. So I ran 300 tests on system A. I ran test number 1 300 times, 60 of them passed, so I passed 20%. I ran test 2, 50 of them, only 2 passed, so I ran 4%, I passed. On the average, we passed about 62 out of 350, which is 20.6%. We did the same thing on system B, and the number come out 8 out of 32, 40 out of 500, and then the ratio, and then the average comes out 9%. Now, here is the interesting thing to notice. System B is better on both tests. 8% passed, 4% passed. 25% passed, 20% passed. Right? If you were just doing one test, test 1 or test 2, in both cases, system B is better. But when you combine the incomparable tested, it turns out system B looks like bad. Only 9% pass as compared to 20%. What is wrong? The wrong thing is that these ratios are not comparable. What is the base here? Right? The bases are not comparable. And so it turns out you can make the number come out anything by having this incomparable basis. If I wanted to show even worse, I could increase, I could change some of these numbers here by some multiplication and then get a different number here. I could run instead of 500, I could run 1000 here and then get even lower percentages. Okay, and so the same example as before, but we just basically the previous example presented in a graphical form. We could have said that test 1 system A is such and system B is such. Test 2 system A is such and system B is such. In both cases, system B is better, but we won't present that data. That data is actually hidden. What we present is we ran 2 tests. And you might even give that number but not present it, the ratios and all that, and then at the end you say, well, system A is 20% and system B is 9%. And so oftentimes these things are hidden inside the graph or inside the data. So this is one way of percentage or ratio. One thing you have to know is the percentage or ratio. Anytime you deal with a ratio, you have to be very careful. But other misuse of percentages. 1000% sounds more impressive than 11 times, particularly in the press. In the press, when they want to make big deal about something, rather than saying this thing is 2 times, they say 200%. 200 sounds like a big number as opposed to 2. 2 is a small number. 11 is a small number, but 1000 actually is a bigger number. Particularly the performance before and after are both small. And so here is another thing. So we asked 2 people here, and we found out that maybe asked 3 people, and they said 2 out of 3 like it. And then we asked in some other place 5 people. So we don't want to tell the world that we just took a survey of 3 people here and 5 people there. Like this is 67% of the people surveyed said this. So you ask, what is the base here? What number 67% is off? Right? And they would have a very small survey, and that would look like it applies to the whole country because it looks like they talk to millions of people. All these surveys that you see from now on, you have to, first question you have to ask is, what is the base? And they tell you on the TV, but they don't emphasize it. And then they will say, the error, this is kind of a standard thing nowadays, because if they say, then people will ask, standard error is 4%. And I will tell you what 4% means is 25 people is all they asked. So, so the thing is that standard error gives up the thing, but people don't understand what 4% is. You know, this written in the corner of the TV that the error is 4% in this survey. But they are very, so same thing is that, you know, so small sample sizes are disguised in the percentage. Instead of saying that we asked 25 people and 1% agreed, or, you know, 5 people agreed, they say we took a survey and, you know, 67%, something like that they will say, because the survey is very small sample size. Third mistake is people use the wrong base. So for example, they say we have 400% reduction in prices. If you have 400% reduction in prices, means you are giving out the money along with the equipment to the people, because the price is negative now. If you reduce something by 400%, right? But that is not the case. This is 400% because in the base, they put the final price. The price was $100 and they reduce it to $25. The reduction is only $75 out of 100, right? So it is only 75%, but instead of saying 75%, they will say, well, the final price is 25, the initial price is 100, so initial upon final is 400, which is wrong. Your base has to be initial, not final. Whenever you talk about the change, the current is the base, not the future. Right? So percentages have lots of other problems. So anyway, having learned about that the ratios can get into trouble, anytime you are forced to take a ratio, you have to be careful, and I will give some guidelines, is that if one system is better on all benchmarks, then contradicting conclusions cannot be drawn by any ratio game technique. Now here, let me just explain that. We are not talking about replicating the benchmarks. We are talking about the benchmarks alone. So replication was another issue which was we saw in the test 1, test 2. Each test was replicated 100 times or 500 times, and you played the game of replicating different number of times. But let's say you just ran the benchmark once, or or the same number of times, and if one system is better on each of them, then it doesn't matter what the base is. You don't worry about it. You move on and you say, all right, because one system is better on both benchmarks or on 10 benchmarks or on every benchmark, then there is no problem. Right? So this is a simple test. Right? If you see that there are different components, and in some component one system is better and the other component, other system better, then you worry about the ratio. If not, then you move on. Second guideline. If one system is better than the other on all benchmarks, a better relative performance can be shown by selecting the appropriate base. Now, so yes, one is better than the other, but how much better? If somebody asks that, then you can play a ratio game. All right? So the example that we had before right here, if you just took the average, you will say 0.75 to 1.25. or 1 to 75, or 58 to this one. So this one looks like 40%. You divide the change, which is 0.42, divided by whatever your base is, and so on and so forth. So this one can be played by what you take as the base. Then if a system is better on some benchmarks and worse on the others, then obviously contradictory conclusions can be drawn. Contradictory conclusions can be drawn in some cases, not in all cases. And so you should work out both ways, right? Write it down, contradictory conclusions. And if the fourth one is, if the performance metric is LB matrix, this is where it is important to know. LB is lower is better. it is better to use your system as the base. So basically, you want to be in the same position in the ratio where the metric wants to be. If the metric wants to be lower is better, then you put in the lower position yourself, means base in the ratio. If it is HB matrix, higher is better, then you put yourself in the numerator and you take the ratio with respect to the opposing party. So for example, when we talked about the instructions, number of instructions, that is what kind of metric is that? Remember the RISC case? Lower is better. So where should the RISC be? In the denominator or numerator? Denominator. And that is where it was. Right? All right. If HB metric opponent as the base, those benchmarks that perform better on your system should be elongated and those that perform worse should be shortened. And now when there is a question of replication, if you have two types of benchmarks, some of them you do better, you make sure that you only do only those benchmarks, 1,000 times. And where you do bad, you do only 5 of them. So when you take the average, it's totally biased. You see what I mean? Not that I am asking you to do this, but you have to be careful when you see a ratios, when you see the performance analysis like that. This we have noticed in real places and real papers. That's why we wrote it down. That, for example, this example is exactly that. So there are two different tests. It turns out that system B is better in both tests, but by multiplying by different numbers, people could even change the whole conclusion. Okay. All right. Now some little bit mathematics. This is a mathematics course, so we have to show you mathematically. So if you have two systems and two benchmarks, the performance is A and A times X, where X is the ratio. The performance of the second benchmark is B and B times Y, where Y is the ratio. If you do the average, your average will come out A plus B by 2. The average will come out AX plus BX by 2. And with A as the base, it will be 1 and X plus Y by 2 bit. And the other slide, next slide probably has the B as the base. So you can figure out all these ratios, and then you will see that what are the conclusions. And the conclusions are that if you just take the raw data and take the average, what are we plotting here? We are plotting 1, 2, and 3 is the ratio of B to average response on benchmark I. So this is the X. Okay? And this is the Y. And this line simply says that over here B is better, over here A is better. So in this little quadrangle, 4 sides, this blue line and the red line. In this quadrangle, A is better on all 3 metrics, all 3 ways. In this little area, which is actually just bounded by 2 lines, B is better on all 3 ways. So ratio game doesn't make a difference. Okay, if you are here, if your X is more than 1 and your Y is more than 1, right here, right, someplace, then it doesn't make any difference, because you will always B is really better. On the other hand, if you are into one of these areas, one of these two, then there is some chance of contradiction. Okay. Here, with base A, you will get this area. I mean, A can be shown to be better. With base B, B can be shown to be better, and similarly here. So basically, that leads to the same conclusion that we had before, and you can do this mathematically and show this, is that you are better off if you take the base as the system where the matrix want to be. If the matrix wants to be lower, you want to be on the lower position. If the matrix wants, but only in this particular zone you can benefit. Okay, is this graph somewhat clear? Is it too much, or basically what we have done is this is the x and this is the y, and the x and y are basically right here. A and AX system, B is x times faster than benchmark I, and y times faster than benchmark J. So if 1 to 1 is right here where A is always better, but then there's a little more area where A can be better, and so this is the whole area. You draw all those three conditions that we have drawn here. AX plus B greater than this one, so this gives you one line, and then that line becomes y less than this. A is better, and that becomes this line. Y is less than 2 minus x. So y is less than 2 minus x is this line. And so you draw these three lines, and then you can see that there are some zones where there is a contradiction, and there is no contradiction. There is no contradiction here. Okay. All right, that brings us to the end of that chapter, and the 5 conclusions are that ratio games arise from the use of incomparable bases. When you have the bases that are not comparable, then you get into this kind of trouble, and the ratios generally do not have to be just taken at the end. They could be built into the metric, they could be built into the performance, they could be built into the relative enhancements or whatever you're measuring. And then percentages are in particular dangerous for that reason. So whenever you see a percentage, you have to know what the percentage is of and whether they are comparable. And then for HB metric, and this is one simple rule which is really interesting, is that you don't need to worry about too much calculation. You don't have to work out two ways. First thing you have to see is whether it is HB metric or LB matrix. If it is HB matrix, then has the person taken themselves on the high side? If they have, then obviously there is a possibility that you could go put them on the low side and make a different result. So for HB matrix, it is better to put the opponent on the base, whereas for LB matrix, you should be in the base. Any question? All right, so the ratio homework. Homework is simple. That should be very simple, straightforward. There are 3 benchmarks, 3 systems, and you take the 3 ratios with A, B, and C, and then conclude which one is better. Now, since this does assume the execution time is, which kind of metric is it? Lower is better. So then you know what you expect.